Okay, thank you. Okay, today we will talk about use after free. I'm not sure if everyone is familiar, so I will talk about the basics first. So today we will uh, look at first the memory layout of a process because it is very important to understand this first before we talk about heap bugs. After this, so this one because I'm not sure if everyone is familiar, I will just go through. And then after that, we will talk about use after free. I will give some examples and some demos. And then after that, we will look at double free. Double free, you can think of it as a special case of use after free. So we'll look at these three things today. And I think this will probably take 1 hour already. So we will look at other real exploits or vulnerabilities and all the different kind of mitigations next time in the next session. Okay, so same as last time, today's the slides just contains the links to the resources. And check them out later. Okay, so let's start by looking at the a program, the memory layout of a program. Okay, so if we have a program like this, a very basic one, and we look at the memory layout inside GDB. Okay, so I will set a breakpoint at min, and then I run. Okay, I'll also show some GDB commands that are useful. So for example, this one, VM map. I think I zoom in more, make it bigger. Okay, you see VM map. VM map means to show the virtual memory map. So the mapping, the memory mapping of this process. So the first thing is this part. This one is the program code. You see there's read and execute. The program code it starts in this address and ends here in this region. And then next is libc. So this one is the program that I write. But we will include the C library, for example, printf from standardIO.h. So this one is we didn't write the implementation for printf because it's in the C library. So here libc is in this section. And then after that, we also have this, but this is not so important to us. And we have the stack over here. So if it's your first time learning about the stack contains the local variables. So now I show you, we write some local variables in this function, in this main function. For example, x equals to 10. And then we also use scanf to read user input into y. And then to show that we have successfully read, we also print it with printf. So when we run the program, it waits for input. So for example, I put 20, then the print what we input. Okay, just a basic program. So now we look at the memory layout again. Okay, so I want to set a breakpoint here lah, after scanf. So I do this. This one is to, so in3 means breakpoint. I write my own inline assembly, put this break instruction. So I build and I run. So first is scanf expects a number, so I give it 100. Then it hits my breakpoint. You see, oh, let me compile with debug. So -g is for debug symbols. Wait, sorry, gcc -g, gdb, and I run. Then I give it 100. You see over here, it stopped at here, but because when you have inline assembly, it doesn't know exactly where the break. It will show you that one line after it. So we have a breakpoint because of this. And now we can look at P means print. So px, it will print in hex. And if I p/d means print in decimal, it's 10. Or p/x also print hex. Then pdy, I see 100, the value that I enter just now. So what if you want to see the address of the variables instead? So I put, so just like in C, when you want to get the address, you put the ampersand in front, and this is the address. And then I want to see which section is this address in. So there are two ways. One, I type xinfo. This is a GEF command. So let me show you if you've never heard of GEF before. You can find GDB enhanced features. So install this to get these special commands, for example, xinfo and vmmap. With this, it shows me that it is in the stack. So our local variables are all in the stack. For example, x is also in the stack. Okay, so you see, address of x is DCF4. Address of y is DCF0. So if you want to see the memory contents, you type tally, so it means telescope. But you can also use dref, so I show you tally. They are the same thing in GEF, like this, or dref. So they are the same. Okay, you see, DCF0 is our y. It contains hex 64 is 100, and then this hex A is x is 10. So another way to look at the content is x means dereference, or examine. Examine 2 word in decimal. So word means 4 bytes, and then D means decimal. And then I also, again, this address. Then I can see my Y. So because the compiler maybe did some optimization, so it put Y in front of, on top of X instead, before X. So it depends on the compiler. Okay, for example, if you want to print in hex instead, 2wx. If you want to print in bytes, so W is word, but if you want to print byte, then B, and let's say X. Like this, you can only print 2 bytes. Or you want to print, if you want to print 8 bytes in hex, like this. If you want to print half word, which is 2 bytes, or we say short in C, is H, so it's half word. And if you want to print quad word, which is 8 bytes together, is G. So this one is GX will print 8 bytes, which is what we see here. Okay, this is the basics of GDB, which I will use GDB a lot in the demos today, because we want to look at the contents in memory when we want to understand all these heap bugs. Okay, so just now we only talk about the stack. Then now we want to talk about the heap. So if you not familiar with C, at least maybe you are familiar with Python or Java. Java and Python, they use the heap automatically for you. So if you have create any objects, you will allocate them in the heap because maybe you'll pass them around different functions. What you see over here in the stack or in a function, once you return from this function, let's say not main, but if you have a function called f, and then we put this inside f, and then we call f here. Then when okay, let me run this. Let me put a few variables here also. Z. Okay. And okay, now you see when I run, again it asks for the number, so I give it a number, and then we have a breakpoint here. Okay, you see here, this is the stack trace. We were in main, and then main calls f, and then we are here. So if you look in GDB, you type BT and look at the back trace, and then it tells us that main calls f. But we also might be interested to know the more information about the stack, because you see here I print address of x, address of y. Same, they are next to each other. C0, C4 next to each other. Then what about z? Okay, you see, we cannot know z because we are in function f. We are not in the same scope. We are in the scope of f. We don't know anything about the scope of main because we are in the scope of f. Okay, then we type frame. Okay. Okay, maybe not so easy to see. Okay, you see the previous frame. So you see here over here again. This one is our frame. It means that it contains all the variables for function f. Over here, you see these two values are the ones that we saw just now. And then this one is the return address, because after we return from f, we want to continue here. So this one is the return address that points to the code here. So this one is the stack frame of function f. Then the stack frame of main is here. You see hex 3E8. You see hex 3E8 is 1000, and ABCDFG is over here in ASCII. You see 61 is A, 62 B, so on. So F stack frame is here, main stack frame is here. And when you use local variables like this, once you return, you lose access to them already, because it is just in this scope. And if you are familiar with other programming languages like Python or Java, maybe when you want to do more, maybe you create an object in this function. So let's define an object. For example, we say car. Then I have give it 8 bytes. Owner, and then maybe integer is color, and another integer is number of or year bought. So when I make a car object here, like this, and then I define car dot owner. I give it a name, me, uh, 3. So 3 because ME and we have a null terminator 0. And then color is a 1. Means and can mean anything. Year what is 2020. Okay. Okay, I hope this compiles. Oh, okay, I need. And let's say you want to return the car from this one. We call it different now. We call it make car. Okay, I delete this easier. Okay. So I want to return a pointer. I want to return this car. Uh, uh, oh, oh, yeah, thank you. Now you see, we put a breakpoint here because I'll show you the assembly for this. You see, when we do return car, what happened is you look at the assembly here. Okay, you see, here is our breakpoint in 3. And then before returning, what it is doing here is copying all the contents in the object. So we see, we step 1 instruction and we see what is inside RAX. It is this. What is this? We're not very sure what is this. Okay, never mind. We go next and we see RDX because after we move this into RDX. You see this. This one is this one, 7E4 is this. So you will copy everything. So if you know do other programming languages before, you may be familiar. This one is called deep copy. This one is, let me see, what is this? Okay, not very sure what. I think this one is, this one is the stack cookie. Okay, never mind. Uh, you see this 656D. 656 is me, the name. Okay. Okay, so this one is deep copy. So when you return, you do a deep copy, but maybe you don't always want to do a deep copy because deep copy is slow. You need to copy everything. You are not, and in other languages we do shadow copy or pass by reference. So instead of pass by value, you pass by reference, means that you return a pointer instead. And how we can do that is here we say that we are returning a car pointer. Okay. So here I print out the address so we can see. Wait, oh yeah, because I have a breakpoint. Eh, wait, we're not very sure why it's new. We find out in the GDB. Okay, you see run, and we have breakpoint here, and then okay, you see now there's no deep copy. You just copy one thing, which is we next. Okay, we see what it return. Oh, okay, I know why. So you see, actually I want to, this is the problem that I want to show you. So, okay, if you want to see the return value, print REX and it's 0. So, so the problem is you cannot return a pointer to something in the scope because when you return from the function, the everything here should be destroyed already. And if you return a pointer to anything in here, it is undefined behavior. It will crash. And I think the compiler knows, so the compiler just return 0 instead of actually the address here. So you cannot. So you see the problem now. You cannot pass by reference if the object is created uh, as a local variable. And that's okay. So here, this one is the motivation. So now we finally can start looking at the heap. So you see, instead of creating a local car object here as a local variable, you need to use this instead. We use malloc. So malloc means allocate. So I allocate an object that is the size of a car. And this one is a pointer. So malloc will return a pointer. Later I will talk more about, I'll show you more. But now I write the code first. Okay, so now we return a pointer that is returned from malloc. And we see what happens. If we run and continue, you see I return a valid pointer now. And you want to find out where this pointer points to. Let me see if we can still see. Oh, I cannot. Okay, so you see we run. Okay, let me give you another breakpoint here. Okay, run. Then we stop here. Hey, sorry. I should put below. Continue. Okay, you see printed this. So we use the same technique like just now, xinfo. Right? Now it tells us it comes from the heap. So here is what happens when we call malloc. Malloc gives us a value from the heap, so it allocates a, a block of memory. Or we can use vmmap, and you see it comes from the heap. So you see, this is the memory layout. It's usually like this: code, then the heap, then the library, but it's very far apart. And just side note, it's very far apart because when you overflow, you cannot write into any region that is useful because it's so far. And then the stack is here. So it's always like this. Okay, so now let's look into the heap. Okay, you see this one, we have it in hex blah blah 2A0 means it is 2A0 inside this region. Okay, let me draw out. Okay, this is our program process. Here is the code. Here's the heap. Here is the stack. So when you call malloc, malloc will take one small part of the heap based on the size that you requested for. Over here, we requested for size of car. So we write like this because you don't want to manually compute the size. But if you want to know what is the size, you can print it. The size of car is 16 bytes. Because here, it takes 8 bytes, then each integer is 4 bytes. So total is 16 bytes. So when you do malloc, it gives you 16 bytes, a 16 bytes chunk. And then when you call malloc again, then if you call with 16, then we will get 16 again. Or if you want to call very big 1000, then it will return a chunk that has 1000. Actually, it's not exactly the value, but you don't need to know the details for now. So usually it will give you multiple of, I think multiple of 8. So 1000 is still okay. But if you ask for a chunk that is, let's say, that is 9, then it will return you 16. Because it wants to align everything by 8 bytes. There's a small detail. Okay, back to here. Now let's look at the chunk in GDB. Okay, so far, is there any question? Because now we'll talk more about the internal structure of the heap, of a chunk. Okay, if you have any question, you can just ask. But if not, I will continue. So over here, we have the address. And then we look in VMMap. It's at 6B0. So in GF, there are a few ways to look at the contents of the heap. First is we can say heap bins. Then I'll talk more about bin. Sorry, not heap bin, because bins are. I'll talk about bins later when we talk about freeing heap chunks. So we have a few chunks. So this one is not our chunk; it's by someone else. And then this 2A0 is the car. Actually, why it should be this? Okay, not very sure why got like this. But I run again. Okay, never mind. So this one, these two chunks are from other people. Then this chunk is our car. You see the size is hex 20. Hex 20 means 32. Although we asked for 16 bytes. This is because inside a chunk, you also will store some metadata. Then you will allocate some extra bytes. I forgot what is the alignment already. Maybe the alignment is 16 bytes instead of 8 bytes. That's why they go up. Forgot already, but this one not so important for today. If you are interested, you can go and search online. So this one is the chunk, and then let's see what happens when we free the car. Okay, so it is important to free memory that we allocated, because if after you allocate the heap, it will keep allocating for you bytes like this, or 128, for example, 128. Then it keep allocating. And if you don't free, means that the program will assume all these memory is still used. So some programs like games or browser, they take up a lot of RAM, and sometimes you are not. People say maybe there's memory leak. So memory leak means the program developer, they write the program, they allocate a lot, but they forget to free. Then the program thinks that all this memory is used, but actually maybe it's not used anymore, but it is still allocated. Then your computer has to allocate your RAM for this program. So maybe it can be quite serious, or you can go 2 gig, 4 gig and use up a lot of your RAM if the program just forget to free. So as a programmer, it's very important to free. Otherwise, it's called a memory leak. So let's say after we free, we see what happens over here. Okay, this one is after first breakpoint. We haven't free yet. Okay, this one is the address of the car. Next, after you free the car, you see okay, you see the chunks like this, and then bins. Okay, now the Tcache bin have one chunk because when you free, it will put inside the bin. So there are 4 different bins. There's a Tcache bin, fast bin, unsorted bin, small bin, large bin. A lot of different bins in this Linux. So the allocator used by libc or glibc is called ptmalloc, I think. Yeah, ptmalloc. I think people say it's well, I'm actually not very expert at this, but yeah, the glibc one is called ptmalloc2, and there are many different allocators. For example, jemalloc is also quite popular, and tcmalloc is so okay, and in many different programs, they also like to write their own allocator. For example, browser V8 allocator, they write their own allocator. They don't use the ptmalloc or jemalloc or what. They write their own. All the big programs, they will write their own allocator. So it means that when we look at this thing, this only applies for glibc, and if you are looking at a program that uses a different allocator, you will have to learn how they handle their malloc and free, or their allocate and free. But the concept are the same. The concept about the heap dynamic memory is like this. When you have allocated memory like this, and later when we free, the typical concept is the free objects are put inside a free list, a list of freed objects. For example, if we want to free this, we put into the free list, and then later we free this one, then like this. So it's a linked list, and then later we free 16 again. It's like this. So the concept is, at least for ptmalloc, is last in first out. So if I free this one last, then I get the next time. Okay, so this one is the start of the head of the free list. So when I call malloc the next time, I will get this, and then I call malloc again, then I get this. I call malloc again, I get this. So this is the concept of free list. And although there are many different allocators, they all will have this. They all will use a free list or something similar to handle their free item. So okay, here we look at a simpler demo. Let's say we allocate 3 items, and these are the addresses. You see, if I free this and then I malloc the same size again, I get the same address. If I free by in this order, 6B0, 6E0, and 710, then next time when I malloc 32, I get the last in, first out. It's like this. And what if I have different sizes? Let's say malloc 64, and then malloc 16 again. And then I free these ones. So I will add them to the free list, which is the Tcache bin. So later we see that it is a free list, keep adding to the list. But there's a maximum for Tcache, which we'll talk about later. Okay, we free everything already. Then now I malloc, let's say 64. So the last one that we freed was 16. But because 64 is bigger than 16, it cannot return us 16. The chunk is too small. It doesn't fit our requirements. So instead, it will give us this second one that we last freed. So this one is this is the concept of the free list. When you ask for malloc a certain size, it will give you the one that is big enough to satisfy. Okay, I hope you over here from this example you can see, maybe you can see what is the problem with use after free already. If you think about it, see if I free it, okay, if I free, let's say this one, but I still hold a pointer to this, then what can happen? So let's look at another example. We extend this example, maybe not car, but a meal. Let's see. Then maybe int is a restaurant ID. And then we give another price like this. Okay, so these two have the same size. This one 8 bytes, 4 bytes, 4 bytes. This one 4 bytes, 4 bytes, 4 bytes, 4 bytes, 16. So both are 16 bytes. So now we look at the situation here. Okay, you see, over here we free the car. So the correct practice is to set car to null point to 0 so that we cannot access this pointer anymore. But what if the developer forgot to do that? Then we allocate a new. Okay, then let's say I set the meal price to $100 ringgit. Then rating is 10. Then the size is very big, or whatever that means. And the restaurant ID is 99. So if we want to print the details of this meal, so now there's nothing wrong yet. Wait, you have to use this syntax because it's a pointer. You see, I forgot to print something. We also look at the print the pointer to see the address of this object. You see, they are the same object, the same address, and the contents are exactly as we said. But what if somehow our code we can still modify the contents of the car, and then I decide to change the uh, color to 0. Okay, then let's see what happens to this. You see, we change this to 0, and the value in the field in the same location get changed also. So now you see, so this one is a standard problem of use after free. So the use after free means I free, but I still use it using after the free. And then the problem with use after free is people will call it type confusion, because you confuse between the car and a new object. So this type confusion allows you to modify the contents of another object in a way that it's not supposed to. But what is this problem? Maybe you think, oh, is a small problem. So let's look at what if you have a function pointer in here instead. So let's say, okay, let me copy the syntax. Okay, I cannot remember the syntax. Okay, let's say the new now, instead of this size, what if we have a ah, let's say we now have a function pointer that is called a, a cleanup function. And let's say we have two cleanup functions. One is cleanup and one is cleanup the premium. So maybe we have decided to initialize this names cleanup function to the basic one. Then for okay, now there should be no problem. Okay, now that we haven't hijacked anything yet, you just see we assign this. So again, if you are familiar already in Python, then you know in Python you can also assign function to another object as a member variable or a field. So we just set to this basic function, and then we call in both printing. But now if you remember, you see at the this is at the last field, And then if you want to change, what if we change the car's last field to this address? See what happens. Okay. Hmm. Oh, okay. Okay. I think it should call. Hmm. Oh, interesting. Why not? Oh, copy wrong. Okay. Let me try to figure this out. Okay, see if they have the same value. Okay, so the problem is, I think they are not aligned because because 8 bytes, 4 bytes, 4 bytes. But now this one is 4448. So I need to delete this to make them align. So it's 8 bytes, 4 bytes. So over here is at the 12th byte, and here is okay, a bit 麻烦. Ah, I know it. We just delete this. So I make it easier like this. So this one is 8 bytes. Long is another 8 bytes. So 8 bytes, 8 bytes. Then here is 448. So this will align with this one. They are at the same position. And then I delete this. Is it okay? It works. So here is what happens is this looks so innocent. You just set the year you thought that we are just setting a value of a car, but because we have a use after free, it also affects the variable that the object that has already taken up that position because they share the same position. And what if this one is value that comes from user input? Then you can get RCE already because you can just change this to another function, another address that can give you RCE. So, but it's not that easy because you have to find the correct address to put in here, and usually you have to do ROP, return-oriented programming. So usually maybe you can. It's not so easy to find a function that gives you RCE, give you a shell immediately. So you have to put in another address and then do ROP to get your RCE. But it is also not very hard if you are already familiar with the techniques. But also there are many mitigations that the developers keep adding to protect programs from these kind of problems, from being exploited through this kind of problem. Okay, so this one is use after free. Now we look at an idea on how we can get a, arbitrary right out of a use after free. Because maybe we are not so lucky. We don't have this function pointer. So we consider the same example as just now. This one is just a normal value. Then can we still exploit this to get uh do exploitation based on this use after free? So there are some techniques. So now we look at this on Tcache exploitation. So I will adapt this one into our example here. Okay, so now we assume that this is a program that allows the user to allocate. So let's say this is a service that takes in some commands and you can do a few operations. For example, create a new car, and create a new meal. Maybe it's you play a restaurant city or this kind of thing. Then you can create new items and then you can destroy a car or destroy a meal or finish a meal. So this one is cost malloc. This one cost free. So now we look at how use after free on this. So now you look at this. It's very basic. It's just some values. You cannot if you get use after free, you cannot exploit because there's no function pointer that you can hijack. It's just a very basic object. But let's say we allow the user to do these operations. I'll just type out here so that you make it simpler. I don't want to do any input output. So I just type out the operations here. And we look at how we can get a, arbitrary right from here. So we look at this example. Okay, so we start off with two objects. Actually, we don't need car and meal. We just have one enough already. So let's say from here, I just allocate two meals. Ignore the car and delete the car. Remove the car. Okay, start here. So we start with two objects. So let's say the user created two meal objects. And then after that, decide to free both of them. But we did not clear the pointers. We didn't do this. So we forgot to clear them. So we have a use after free. And let's see what to do next. Okay, let's say we have a target memory location to override. For example, we have this integer, we call it a target. And it contains this value currently. So we just print out the addresses to make it easier to see. Okay, then I set a breakpoint here so that we can start looking at what is inside. the heap, the bin, the Tcache bin. Okay, we have a breakpoint here. Okay, you remember we have freed these two already, and their values are 2A0, 2C0, and we want to have an arbitrary write. So we want to get the arbitrary write primitive to overwrite, so that later we can overwrite the contents in here, which we is not supposed to. So see, let's look at the chunks first. Again, you have a few chunks. These are from other parts of the program, maybe, but these two are from us. You see, this one is our first meal, and this is our second one. Okay, let me assign some value so that it's easier to see the contents. Let me put this to be like this and this, so that we can distinguish in memory which one is which one. Don't care about the other fields, not so important. We run and then we hit chunks. Okay, look at this first. We run telescope and we see, oh yeah, there I put the values. I'll put more also. Just a few dummy values. I just put this number so it's easier to see. Yeah, you see, okay, this is our chunk. Our first meal is this. You see, 4444 is this one. 5, 6, and 7. And then here we got this also. Okay, so now the question is, what happened to these three values? They changed to other things already. This one is, so what happens is, when we free a chunk, the allocator will change the first 16 bytes to store the metadata. And actually I forget already what is the metadata of all of them. Let me try to remember. For example, okay, so these ones they are encoded, they encode this flex. And this one should be one of them should be the next, is to say is the next chunk. So, oh yeah, okay, there's another problem, but we talk about that later. So this should be, because we free meal 1 and then free meal 2, so this meal 2 should be the, you see, heap bins. The second meal, you see the second one is 2D0 and first one is 2A0. So 2D0 is at the start, and then 2A0 is the, Is it? Yeah. 2D0 will be allocated first next and 2A0 later. So you see it's a linked list. So these values, you keep tracks of what is coming next here. But because they want to protect from exploitation, they do a bit of shifting to change the values. So by right, mil2 should point to mil1. But this address is not the same as this. And there's a documentation somewhere. Try to find. Okay, this one will be the last thing that of today's sharing. We will continue double free next time. Thing is this one. No. Hmm. Hmm. I forgot which one I think is. Okay, give me a few minutes. Check the history yesterday. Ah, forgot where I get this link from. Oh yeah. This one. Not this one. Okay, never mind. I'll put the link in the Google Slides. I forgot where I get this link from already. But this it's called protect pointer. You see, they do this. They take the pointer, right shift by 12, and then XOR by the pointer itself. So if you want to get back the value, you just reverse this, which is review pointer is we do the same thing. Take protect pointer, which is the address of the pointer and the value of the pointer. Okay, we'll take this one. We want to review this. So we take this tx, this right shift by 12, XOR with this. Yeah, you see, we get the link, which is this. So mil2 contains a pointer to mil1. We have to do this to get this. Okay, now you see what we can do with this use after free. What happens if we override this pointer? Because we actually have access to this pointer. Again, let me modify the structure a bit so that it's easier. Make it long so that it's 8 bytes. Yeah, we compile this. Okay, we set a breakpoint here, and then what if I take mil2 and I change it to okay, need to do some nets to calculate because I want to change this pointer to make it to address of target. So I need to take the original value XOR by address of nil2, which is this, right shift shell. And let's see if we can corrupt the free list like this. Not oh. Okay. Okay, so here we see the heap bin, nil2 and nil1. Then after we overwrite this, let's look at the heap bin again. Oh, corrupted chunk. What happened? Because okay, I'm not sure if I overwrite correctly. But let's see. If I take wait, I need to let me see. Oh, sorry. It should not be this. It should be okay because the goal is to change the protected pointer to address of target. But I didn't even mention target over here. Okay, right now protected pointer equals to, we saw just now, this is equals to this, what is inside here right now, just now. Then reviewed pointer is this XOR with this. So it's what we did just now to get 2A0. The target protected pointer is address of target XOR new to this. Okay. Actually, I don't put this. Put this. Okay. Okay, so you can see heap exploitation. We always have problems like this where you have to calculate the addresses. If you do pwn in CTF, or if you don't do pwn in CTF, then you always see people do a lot of calculations. So this is why. Okay, the target is this address. We want to overwrite this. And we managed to let nil2 point to here already as the next chunk. So you see what happens now. Now I do a malloc again. I do a malloc, and then we see what's inside. Yep. Okay. Corrupted chunk, and then now we malloc, and we see what is inside here. Oh, the next chunk in the free list is our target. So what if we do another malloc Then we see what is the address that we get for mil1. And we compare with the address of target. And also let's change the first field to something else, like this. Okay, we also want, okay, so see what is the value inside target before and after. Okay, now I comment out all the breakpoints because we don't need anymore. Wait, never mind, I keep it. Okay, we run, then we skip through all the breakpoints. If not again. Oh, and put a breakpoint here so we can see the output. Okay, now we are before printing. Then we malloc, and then we print the pointers, and we change the value, and we see what happens. Oh, unaligned Tcache chunk. So, right, the problem now is because, oh yeah, the problem is it ends with 8. Then it doesn't like it because it's not aligned. I think it needs to be 16 byte aligned. And we have to make this work. I just add another variable just to fill up the space for alignment. Then we see it's not aligned also. Wait, I have to align it myself. To align, I will end with. So I just do this, means I set the last nibble to 0. Okay, we're done soon. Wait, okay, there's a problem with the GEF command, but we are eh? Okay, something. Okay, it's not correct. I need to add more F. Okay, because the address is longer. Okay, finally, we have aligned chunk. So when we continue, we don't have error. Let's see what we get. We get, ayo, I forgot to get to this. So our mil is here and target is here. See, it's a bit off because I have to add the alignment. I have to let be aligned to 0. So now, just now we were this value, and now it's 0. Why? Because I think what happened is when we do malloc, when you malloc and want to remove it from the heap bin, you see, removed it from the heap bin. But when you remove it from the heap bin, it also needs to update the metadata that was in the chunk that we see just now. Okay, I cannot show, but you can think about it. In the chunk, the metadata has to be updated. So maybe because of something we set to 0, but we can still set it to the value we want, because if our mail1 starts here and we want to modify CD8, then that would be this value. And it's this is the value we set. So we overwrite, we managed to overwrite the value in the target location. So this one is, we managed to get the arbitrary write from UAF. So do we just stop here, or can we do more? Okay, so here's the last part. Instead of just stopping here, by just overwriting one variable, how can we get RCE? So let's say we have make it simple. It's like standard CTF style. We have a win function that gives a shell. Okay, never mind, just print. So what if we overwrite something else instead? Okay, then now let's look at the stack again. Let's look at frame. Info frame. Okay, again, this is not very useful. I just type telescope RSP, which is the stack. So you see, this is our stack. And this is mail1 pointing to here. And this is this. And then let's see what's in the stack. Blah, blah, blah. This one is let's see which one is the return address. Return address should be here. Let's go back, because main will return to libc start call main. So this is the return address. So what if we change this value instead? Okay, so we need to do a bit calculations. I think I need to modify this a bit more to make this work again. Okay, let's see. This is here. This, then 1, 2, 3, 4, 5, 6. Yeah, I just add. Okay, 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Okay. Make it easier, I call this return. Okay, so now instead of just modifying target, do even more. I set the return to the win function, and set a last breakpoint here. Mm. Delete. Okay. See first. Okay, corrupt. Here is we corrupted the tcache free list, the tcache bin, and then we malloc. So malloc, and then now tcache bin is pointing to our target address. We get our target address and we modify the stack, some contents in the stack. And lastly, we want to do this. We want to modify the return address. Let's see what is inside the stack. This is the return. Okay, so we slowly step and see what. Okay, see the return. We return into win function because we overwritten the return address. So to summarize, okay, so that's all that I have for today. To summarize, even though you have a use after free that looks very innocent, just very normal fields, no function pointer, you can corrupt the free list and then get arbitrary right. And arbitrary right, you can override either other function pointer, or you can, if you know the address of the stack. So this one you will need information leak. You need to know the address of the stack. After you override, get an arbitrary right, you can, and if you know the address of the stack, then you can override the return address and get RCE. And there's another technique, if you are interested, that I saw just now here. This, you see, exploit a UAF to gain leakless control. Because just now I say you need a leak of the stack address. You see over here, I know the address of target, but in a real program, maybe you don't know because you don't have a information arbitrary read exploit. Then you cannot do this. You must know the address. Only then you can do this. And this house of water, say you don't need leak. So if you are interested, you go and read. But this one is very long, so I will not go through. This one is 400 line. And if you're interested, you can look at it yourself. Uh, yeah, one last thing. So you see over here, just now, I keep having to change the struct so that it can align properly, or it can align with, it is big enough to override the parts that I want to override. And usually in heap exploitation, maybe you hear this term before, it's called heap feng shui, is to find the manipulate the layout of the heap. Okay, this is not exactly what I'm doing. So heap feng shui, do heap grooming, it does more than this. It will allocate a lot of things in the heap, and then you free again, then you make the heap appear in the correct layout. Maybe you have some holes here and there, and then uh modify the heap until you can do the things that you want. And that's all for today. Next, so we do this once every 2 weeks. So next Tuesday, we continue on double free. See if you all have any questions. Oh yeah, so I forgot to say about this. Usually in heap exploits, the exploit person will have to, the attacker will have to find the correct object structs that are of the correct size and correct layout inside, so that they can do uh what we are doing here, find the correct size and correct layout. Mm. Yeah, no question then. Mm. Okay, thanks everyone. We will continue fifth. Or got question? Okay, but anyway, we continue part 2 on 4th June, next Tuesday. I think we will also have part 3 because I also will share about the mitigations and how modern programming languages will help protect developers from making these kind of mistakes. Well, I think that is more relevant to most people lah. I think the exploitation, most people will just learn for exposure. Same for me. I also just learn for exposure and for interest.